Okay. So today we continue to study the properties of the action of a Gaussian strong random operator on the random elements in Hilbert space. So let us start from the recalling what we did last time. We considered Hilbert space H, which is real and separable. Hilbert. We consider here the white noise, Gaussian white noise in this space. In H. We suppose that in our probability space, sigma field of random events is generated by the white noise psi. And this gives us possibility to use all tools from stochastic analysis like E-to-Wiener expansion, stochastic derivative, extended stochastic integral, and so on to study the random variables, random elements, and random operators in our space H. Then we define Gaussian strong random operator Gaussian strong random operator A in H as a continuous linear mapping. A is acting from H to L2 omega pH to the space of square integrable random elements in H. Such that A of U is Gaussian for all U which belongs to A to H. Moreover, we suppose that it is jointly Gaussian with psi. We already have seen that such object is not in general a family of bounded linear operators in H, which is indexed by the elements from our space omega. So we discussed possibility to define the action of A on random elements in H. Main example for us and main motivation for us was the construction of the extended stochastic integral, because as one of the good examples of the Gaussian strong random operators, we have the operator of integration with respect to Wiener process in the space of square integrable functions. And in those cases, we have seen the construction of extended stochastic integral. Our construction is generalization of those. In our case, operator A can be represented as follows. A of u is equal to alpha 0 of u plus alpha 1 from u and psi. Here, alpha 0 is an element of the space of continuous bounded operator H. This is deterministic operator. One can formally write that alpha 0 is equal expectation of K. This is just formal expression, but it is useful, and sometimes it has a rigorous sense. Then alpha 1 is a bilinear form from elements from H and H, and has the following property. This map with respect to the first coordinate is mapping from H to Hilbert-Schmidt operators in H, linear and continuous. Okay, so we have such a representation for any Gaussian strong random operator which is jointly Gaussian with psi. Then we take the random element x in H. So x is square integrable random element in H. Then we know that it has e to Wiener expansion. So x is uniquely represented by the series from n equals 0 to infinity bn psi psi psi. Here bn is symmetric h-valued Hilbert-Schmidt form. On H. We also have the very good expression for the second moment of x, namely if one look for the expectation of the square of the norm of x, it's equal to sum from n equals 0 to infinity n factorial. Here is norm bn n square. This is the Hilbert-Schmidt norm exactly in the space of h-valued Hilbert-Schmidt forms on H. We will define, we already defined the action of Gaussian strong random operator on X using this e-to-Wiener expansion. Namely, we considered following forms. for all n which is greater or equal than 0. We consider it alpha 1 from Bn, phi 1, phi n, phi n plus 1. And now we get Hilbert-Schmidt form from n plus 1 variables. But this Hilbert-Schmidt form evidently is not symmetric because alpha 1 has no any relation to this element, so we cannot expect symmetricity, but one can consider its symmetrization. So lambda alpha 1 Bn is symmetrization. Then we defined the action of A as element X. So by definition, it is equal alpha 0 of X. Here there is nothing interesting because this is simply application of continuous deterministic operator to X plus the sum from n equals 0 to infinity of lambda alpha 1 Bn psi, and here we have n plus 1 arguments. And substitution of, let me recall, the substitution of generalized random element psi here is expressed by Hermite polynomials and special sums. We already discussed this. So if such series converge in square mean, then we say that this is the result of action of our Gaussian-Strong random operator on the random elements X. As an example, we considered construction of extended stochastic integral, and we have seen that this is exactly those construction in the last lecture. So now we continue to study properties of the action of a Gaussian-Strong random operator on the random elements. As we discussed already, and as we expect actually, this action is not bounded. It means that not for any square integrable random element X, this series must converge. So we already discussed that if we consider domain of operator A, which we define as a set of all square integrate random elements X for which this series converge, then this what we know about this domain. Of course, this domain contains all polynomial random variables. So such random elements X for which we have here a finite sum. So which have finite e to Wiener expansion, like X equal to sum not to infinity, but to sum n capital Bn psi. Of course, there are no any problems with convergence, and such element definitely belongs to the domain of A. Since then, one can say that domain of A is dense in A2 omega P H. And the natural question is which properties have A as unbounded operator on this space. And we already stated last time that A is closed operator. Let us prove this lemma now. So we have such a lemma that A acting from dA to A to omega H is closed. The proof. Let me recall you what we have to prove. We have to check the following thing: that if xn, the sequence of random elements, converge to some random element in L2 union, and n tends to infinity, and xn belongs to domain of A for any n which is greater or equal to 1, and A of xn converge in L2 union to some y random element and n tends to infinity, then we must have the following conclusion: then y, excuse me, not y but x belongs to domain of A, and A of x is equal to y. So we have to prove this. How I will do this? Actually, to prove these two facts, I can use Ito-Wiener expansion. Of course, I definitely have to use it in order to check the first one. And then I can use Ito-Wiener expansion as follows. Just consider Ito-Wiener expansion of right part and left part and compare the elements. If the elements will coincide, then I can say that everything is okay. So let's start. First of all, let me say some simple, general and useful remark. Suppose that we have zeta n, which in random elements which converge in square mean to the random element zeta when n tends to infinity. Suppose that zeta n has Ito-Wiener expansion, like the sum from n equals 0 to infinity. Cn, oh, excuse me, maybe m here will be much more rigorously. M and n is corresponding to this index, n is corresponding to summation xi m arguments. Zeta itself has the Ito-Wiener expansion like Cm xi, again m. Then for any m which is greater or equal than 0, norm of Cm minus Cm, here is m's norm. So again, let me repeat, this is a norm in the space of m linear symmetric h-valued Hilbert-Schmidt forms on our space H. So this norm tends to 0 when m tends to infinity. So we have such a useful conclusion from this convergence. Actually, it is not hard to understand why this happens. We already discussed with you that summands here are orthogonal. And this one summand is corresponding to the projection of zeta n on the linear space generated by such forms. Yeah. So one can expect this relation because it simply means that we, from this convergence, we have convergence of projections. But if the language of projections is very abstract, then one can just write the expectation of the difference between this norm of the square of the norm of difference between two these random elements. Let me write it. By the properties of interlinear expansion, expectation of norm zeta n minus zeta square is equal to the sum from n equals 0 to infinity n factorial, and here we have the same difference Cmn minus Cm m squared. Now we know that this expectation goes to 0. So we know that it tends to 0 when n tends to infinity. From here, our conclusion follows. Okay, so we have such a useful property, and now let's use it. Let's come back to our situation with the operator A and random sequence of random elements xn. So now I will suppose that our operators, our random elements xn, has an interlinear expansion like this, sum from m equals 0 to infinity, bn n psi. And our limit random element is the interlinear expansion like this one, bm psi, and our random element y, which we already have in the statement of the lemma, has interlinear expansion like sum from m equals 0 to infinity, Cm psi. Now let's begin to work with it. To make our work slightly easy, I just will suppose that alpha 0 is equal to 0. Why this is not a restriction? Because we remember that alpha 0 is just deterministic bounded operator, bounded linear operator. So we can lift its action to L2 omega fp with any problem, and we will have a sum of bounded linear operator plus something. And if those something related to alpha 1 is closed, then adding the bounded operator does not change the situation. Since then, I will suppose that from now alpha 0 is equal to 0, which make our formulas shorter and easier. Okay, now let us consider our random operator A, which has a representation A of u is equal alpha 1 u xi, and let us consider the action of A on the element xn. To do this, we have to make symmetrization. So to define the action of a random Gaussian strong random operator A on the random elements xn, we have to make symmetrization of the following kind. We have to consider lambda of b, excuse me, lambda, here is alpha 1, b, m, n, and here is a. So here inside we have m arguments, and here we have additional 1 argument. Since alpha 1 is a continuous linear operator acting from H to the space of Hilbert-Schmidt operators, one can easily check from the remark which we already did that this goes to lambda. This goes to lambda alpha 1 bm. Yes, because of continuity of alpha 1 and because of the remark which we did before. It is related to the convergence of this form bmn to bm under n tends to infinity. So I just apply continuous linear operator 1 and symmetrization, which is also continuous operator in the space of Hilbert-Schmidt form 2. So we have such convergence. Right? Okay. Okay. From other side, let me recall you that we have the condition that A xn converge in L2 to some random element y. Yes, and we already wrote the e-to-winner expansion for y. It is like this one, Cm xi time. So one can see that these elements must converge to elements of e-to-winner expansion of y. So from other side we have under n tends to infinity convergence to Cm plus 1. Yeah, m plus 1 because of this additional argument. So we have such convergence, this one and this one, in the space of Hilbert-Schmidt forms. Because of it is a good Hilbert space, we have the equality. And what we proved? We proved that if we take the elements of it with the expansion of our random element X, make symmetrization after application of alpha 1, then obtained series converges and give us the element Y. So from this one can conclude that now X belongs to domain of A, and A of X is equal to Y. So we proved our statement. Really, the action of Gaussian-Strong random operator is closed in the space L2 omega. Let us continue with the properties of this action, and we will actually, our goal is to study equations with the Gaussian-Strong random operator, and it will be useful to have the formula of substitution of the random constant into Gaussian-Strong random operator. Let me recall you that we have a very good property of extended stochastic integral. So let us consider the following example. Consider a random constant under the sign of extended stochastic integral. Maybe I will use the following space L2, 0, 1 as the space H. I will suppose that our Xi is the formal derivative of the linear process W, and as Gaussian-Strong random operator, now I will consider the stochastic integral with respect to W, even with the fixed time horizon. So now as A of X, A of U, firstly, A of U, I will consider integral from 0 to 1, US dWS for U which belongs to L2, 0. We already know that this is unbounded random operator, so this is a really example of a Gaussian-Strong random operator. In this case, Gaussian-Strong random functional, and we already defined the extended stochastic integral. So now A of X is well defined for some X and is extended or скороход stochastic integral. Okay. And we know the following very good property. If we consider alpha is a random variable, then we have such a nice property. We have such a nice property that integral from 0 to 1 alpha xs dws. So what we have here, we have Skorokhod integral from alpha multiply on xs. It is equal to, here is a dream of bad students. Yeah, simply take out this random constant from the integral and forget about everything. But we cannot do this. We have to add the next term, and the next term is like integral from 0 to 1 d alpha s ds. So, oh, excuse me, xs ds multiply on xs ds. Of course, for this formula, we have some restriction on alpha. For example, alpha is bounded, d alpha is bounded, and so on. But the relation has the following form. We have a nice formula with this stochastic derivative of the random variable alpha in the right hand side. Okay, so we have such a good expression for Skorokhod integral, and since we already said that the action of the Gaussian strong random operator on random elements is generalization of the Skorokhod integral, then it means that maybe we must have also a good formula for general case. So now our aim is to consider the following question. To consider the following question, we have x which belong to domain of Gaussian strong random operator A, and we just have some random variable alpha, and now consider alpha h alpha x. What it is? If we, of course, suppose that alpha is such that alpha x is in the domain of the Gaussian strong random operator. For example, we can begin with such a case when x is stochastically differentiated. You remember last time we get the statement that stochastically differentiated random elements belongs to domain of Gaussian strong random operator A. So suppose x has stochastic derivative, alpha is bounded and has stochastic derivative, then the product by the chain rule also has stochastic derivative and belongs to domain of A. But what we have to write here? This is the question. And to have the answer, let me start with the simple examples. Yeah. Let me start with the simple examples. The first example actually is the same as the Skorokhod integral, and we discussed this last time. I only consider the formal and abstract situation. So let me consider the H of U, which is the product with our psi. Yeah. So this is random functional. We already discussed that this is unbounded random functional, and actually, let me recall you, just in case h equal to 0, 1, H equal L201 and this psi is formal derivative of W, then in this case A of U will be equal the integral from 0 to 1 to S dWS. So this is the same example as before, but I just draw it formally, yeah? In abstract situation. Okay. So now let us consider the answer. We know it already. So the answer is now the following. Psi multiplied by alpha x is equal to alpha psi x, which is defined as we define it, minus here is d alpha x. This is abstract form of the formula which we already discussed for extended or square-root stochastic integral. But now let's write this formula using orthonormal basis. Yeah. So I will suppose that En is orthonormal basis in H. Then one can consider this expansion via this basis for our random functional. So A of U is equal to sum from n equal 1 to infinity series psi En and U En. Yes. Now let us suppose that our random element X has a finite expansion with respect to En. Yeah. So it looks like n equal 1 to capital. Here is xn, xen. Yeah, that's all. Then let me write what happened if we apply the previous formula. So now alpha x is still the element with finite expansion, finite dimensional expansion with respect to our basis alpha x En. Yeah. And finally, what we have now, we have that A of alpha x is equal to alpha on the sum from n equal 1 to n. Here this is psi En x En minus here we have sum from n equal 1 to n capital. Here the scalar product d alpha En x En. Yeah. Okay. Now the last what we did will be in consideration of one summand at every sum. Yeah. So from all of these considerations, we understand now the following interesting property. That if I consider very simple is equal psi en multiply on u, then a alpha x will be equal alpha psi en x alpha psi en o u en. But here we can not write it, just xn minus d alpha en x. So we have very simple random operator, and then we have such expression. Now let's consider general case. Let us consider general case. So now consider the Gaussian-Storm random operator A. Again, I will suppose that it has 0 mean, because it is not very important for us. So I will suppose that action of A has the following expression. This is alpha 1 x. Excuse me. I already suppose. Okay. Here is psi. Here is psi. Okay. Then, if we have such x lemma, if x belongs to domain of A, alpha is a random variable such that alpha has stochastic derivative. I recall you that we just denoted by W1 the elements, the random variables which has the first stochastic derivative. And alpha x also belongs to dA. Then we have the following. A from alpha x will be equal alpha A of x minus, here is alpha 1 x d alpha. This is an expression for substitution of the random constant from the sign of the Gaussian-Storm random operator. You see, actually it repeats what we did with the examples, and the proof also will use the previous examples. Yeah. Okay. So the proof. Let us suppose that we have En is orthonormal basis in H, and suppose that we consider alpha 1 u H is equal to the sum from n equal 1 to infinity alpha 1 u en, and here is h en. Yes. Then h of u, a of u is equal to the sum from n equal 1 to infinity. Here is alpha 1 u en, and here is psi en. You see that now the action of Gaussian-Strong random operator on the non-random element u is described via multiplication on the product side and element of basis, exactly as in previous examples. So now maybe I can use previous example and write what will happen if we just try to apply our random operator to alpha x. So due to this expression, if I take just one summand, I will get so alpha 1 alpha x en multiply psi en and what I have to do, I have to write minus as before and put here alpha 1 x en and here d alpha en. To get the final answer, we just have to make a sum from n equal 1 to infinity. And then we get the desired formula that now the substitution of the random constant is like follows: alpha a x minus alpha 1 x d alpha. So we have such a nice formula related to the restriction, to the possibility to move the random constant inside of the extended inside of the Gaussian-Strong random operator and outside. Yeah? We have such formula, and we will use this formula in the future when we'll consider the equation with the Gaussian-Strong random operators on the next lecture.
I have a question.
Oh, okay. Exactly to the end of the lecture. What is your question, please?
Oh, my question is, what did you just use? Did you use the example that we did?
Mm-hmm.
But what example special for the case of the stochastic integral?
Of this one, yeah.
Yes.
Actually, what we have to do, we have to consider simple, very simple Gaussian-Strong random operator an of u, which is equal alpha 1 u en, and here is psi en. And this operator is exactly as one coordinate in the previous case. Yes, in previous case, instead of this one, of course, we have simply u-en. Yes, this is just difference.
Yes.
Yeah. So the same happened when we substitute here x alpha x. Then we have here firstly alpha x, yes, exactly as in those examples, minus, and you remember in the example we have the derivative of alpha instead of psi.
Yes, but the example was not proven, right? You just said it is exactly as in the case of stochastic integral.
No, you can prove it very easy. I just use finite. I just use x, which has a finite expansion. Yes, but you can take x, which has a expansion of such kind. You can consider just one x en. Yeah, you can just take n fixed from the sum. Then you will have this one. Yeah, just once a month, and you will have the same.
Okay.
Yeah. So this is just algebra. And I said that you can take one coordinate. It is exactly what we need.
Okay, thank you.
You're welcome. Maybe other questions? I have a good news. This boring stuff will end next time, and we will consider interesting things with the equations with Gaussian-Strong random operators. We already prepared all technique. So thank you for attention, and see you next week. Bye.